Hypothesis tests can also be conducted on a binomial proportion, and so I'm going to be talking about that in this screencast. Let's start with an example. A set of 200 independent patients take antacid medication at the start of symptoms. So this is a clinical trial. 80 of those 200 experience moderate to substantial relief within 90 minutes. Historically, only 30% of patients experience relief within 90 minutes with no medication. So this is sort of like a negative control. With the medication, the probability of experiencing relief is 80 over 200, which is 0.4. But historically, only 30% of patients have experienced relief. What we want to do here is we want to statistically show whether or not the antacid medication helps to relieve the symptoms. This problem represents binomial trials because we have patients are our trials and we have a probability of success or failure. So if the true proportion is 30%, this is sort of our null hypothesis, then the distribution looks something like this. If n equals 200, it's centered about 60. This shows the probability distribution function based upon that 30% in a population of 200. So we can set up a hypothesis test. The null hypothesis is that the proportion is 30%, which is our historic value. But if we want to show that the antacid medication helps to relieve these patients, then we can hypothesize an alternative hypothesis, p is greater than 0.3. If we can show that our sample 80 out of 200, lies somewhere up in a tail that has alpha percent, and in this case we're going to use 0.05, then we can accept the alternate hypothesis. And just looking at this distribution, you see that we have 80. 80 is very rare, and when we do this, it's actually 80 and above, so we would tally that. So just looking at this graphically, it appears that we can accept our alternate hypothesis. However, we need to calculate actual numbers for this. The book goes into a method called the normal approximation to the binomial. So we can set up our null and alternate hypotheses. Now, before we use the normal approximation, you have to make sure both of these conditions are true. N times p has to be greater than or equal to 5, and n times 1 minus p has to be greater than 5. P in this case is 0.3. 0.3 times n, which is 200, is 60, and 60 is greater than or equal to 5. The second condition, 200 times 1 minus 0.3, is 140, and that's greater than or equal to 5. So we can use the normal approximation to the binomial distribution with no problem. The test statistic for this normal approximation is given here. We take x. X is the number of successes out of n that we actually observe, minus n times p naught. P naught is our null hypothesis, divided by the square root of n p naught times 1 minus p naught. By the way, this is exactly the same as the following. If we divide everything by n, and our experimental observation is p hat, so in this case, p hat is going to be 0.4. We got 80 out of 200 patients who experience relief with the antacid medication. And since this is an upper-tailed test, we can accept the alternate hypothesis if z naught is greater than z alpha. We're going to use alpha of 0.05. If this is true, then we can accept the alternate hypothesis. So let's go ahead and do this. We calculate our test statistic, z naught. We plug in our p hat of 0.4, subtract the null hypothesis, the proposed proportion of 0.30, and we divide by p naught times 1 minus p naught over n. We get a test statistic of 3.09. Now obviously 3.09 is much greater than z of 0.05. We're comparing 3.09 to 1.64. So we're way out in the tail of this distribution, the right tail. And so we can support the alternate hypothesis and reject the null hypothesis. If you calculated a p-value by using the norm.dist function in Excel, you would calculate that the p-value is very small. It's 0.001 approximately. Now keep in mind this is an approximation, so this p-value is not quite as good as we get using a second alternative. The second alternative to solving this problem is the direct binomial approach, and that is we just use Excel to calculate probabilities based upon the binomial distribution. Here we have n equals 200. This is based upon the null hypothesis of p equals 0.3. The area including 80 and beyond is known as the p-value. And so we can calculate this p-value. So it's 1 minus cumulative up to and including 79. That's the probability that we get 80 or above successes out of 200 if the true proportion is 0.3. And we calculate that to be 0.00164, which is really small. And this is the p-value. This p-value is more accurate than the p-value that we got using the normal approximation because this is an approximation and not exact. Let's go through a second example real quick. Your friend boasts that she can successfully ride a certain mechanical bull for at least 8 seconds, 75% of the time. So that's the null hypothesis. You're calling BS and you feel that she's not quite that good. Over the next couple weeks, she attempts the mechanical bull a total of 10 times. Of those 10, she stays on 6 times for more than 8 seconds. Can you prove using a significance level of 5% that her claim is wrong and that she can't ride the bull 75% of the time? So our null hypothesis, probability is 75%. You think it's significantly less than 75% of the time. You can use the normal approximation if the following are true. But in this case, you cannot because n is only 10, p is 0.75. While this first equation is true, the second one is not true. 10 times 0.25 is 2.5, which is not greater than or equal to 5. So we cannot use the normal approximation to the binomial distribution. That's no problem because we can use Excel. Let's go ahead and solve this in Excel. I've just set up a spreadsheet here where I have n, the total number of trials, 10. Probability of success is 0.75, and this is the probability of 0 through 10 successes out of those 10 trials that she performs over the next couple weeks. She rides the mechanical bull successfully 6 out of those 10 times, and so what we're trying to do, the p-value, is essentially the area in the tail. This is going to be in the lower tail because it's on the left side of the distribution, comprised of 0 up through and including 6. We can calculate a p-value. That's just the binom.dist function, 6 successes, so up to and including 6 out of our n trials, 75% probability of success, and we're going to do cumulative. And when we do that, the p-value is 0.224. We haven't quite proven that she can't ride the bull 75% of the time. We would have to be down in this tail down here. And in fact, we would probably have to be closer to 4 successes out of 10 in order to show that her claim is false. So our conclusion then, our p-value is 0.224, which is greater than our alpha of 5%. We reject the alternate hypothesis and we fail to reject the null. We can't prove that her claim is incorrect. Thanks for watching.